please remember that.
Okay, the next talk will be by Justin Pombrio about hygienic resugaring of compositional desugaring. So let's
take the speaker. Thank you. Hi, I'm Justin. Oh, I should put the microphone on. Do you still have the microphone?
Oh, sorry.
Or else this isn't going to be recorded. Hello? All right, so hi, I'm Justin. So before I start, let me say a word about syntactic sugar. So syntactic sugar is ubiquitous in programming languages. It's very common. The mic? Can you not hear? Maybe if I put it up a little higher. Is that better?
Yes.
All right, how's that? Can you hear? All right, great. All right, so syntactic sugar is very common. It appears, for instance, in macros in Racket. It appears in Haskell. List comprehensions are defined in terms of syntactic sugar in the standard. For Pirate, which is an educational language being developed at Brown, we make heavy use of syntactic sugar because it's just a good design decision. And I'm sure you've seen lots more examples. Now, since I'll be talking a lot about desugaring, it'll be helpful to distinguish between the language before desugaring, which I'll call the surface language, and the language after desugaring, which I'll call the core language. All right. Now, this talk is going to be split into 3 parts based on 3 of the words in the title. Let me start with resugaring, the word you probably haven't seen. All right, so the idea of resugaring is we're going to start with some surface term in a language, and we'd like to see an evaluation sequence that shows how T runs step by step. So what actually happens when you run T is that first it desugars into the core language to some T1, and then T1 takes a bunch of evaluation steps in the core language. Now, when I say evaluation steps here, I'm not going to care about the details of how that happens. In fact, this can be any transition system. Okay, so we want to show some evaluation sequence for T. Now, one thing we could show is we could just show the sequence T1 through T4. But notice that that's a huge leak of abstraction, because the whole point of syntactic sugar is that once it's defined, it should be invisible to programmers, whereas here it's all exposed. So the question of resugaring is whether we can take this evaluation sequence and present it using the syntax of the surface language. All right, now what are some use cases for this? So the most direct one, perhaps, is to build an algebraic stepper. So here, for instance, is the algebraic stepper for Racket's beginner student language. And with resugaring, you can basically take an algebraic stepper over a core language and get back a stepper over the surface language by resugaring the terms. And there's a bunch more cases where this sort of problem shows up. Basically anywhere where you've got on one axis desugaring and on another axis some transformation, and then you want to show terms again. All right. So that was a very high-level overview of resugaring, but let's look at a concrete example now. So for this example, I'm going to introduce a sugar. It's going to be the OR sugar. So I'll use this as a running example throughout the rest of the talk, so take a second to look it over now. So basically, X or Y should desugar into an if statement that tests X and then returns either X or Y. You need to add a let binding to make sure that X doesn't get evaluated twice. All right, so now for an example of resugar. So here's your surface term, not true or true. When you actually run this, it first desugars to the core language using the expansion I just showed. And then it takes a bunch of evaluation steps. So first, not true simplifies to false. then the t gets replaced by false, and finally the if evaluates to its else branch. Okay, so the question now is how should this be presented in the surface language? So let me go through a few different attempts and ask you what you think. So here's the first attempt. So what if we showed this as the first step in the surface language, where this is the second core term just copied over directly? What? No? Ooh, all right, I'm hearing a lot of booing. I'm guessing that the reason is that this kind of breaks the abstraction where we started with a term that showed or, and now we've leaked all the details of how or is implemented. All right, here's another one. How's this? Yeah, it doesn't actually show anything. We actually want to see some steps. All right, and this one? One last attempt. Yeah, I heard a watt in there. It's a little strange. This second or came out of nowhere. And this doesn't actually correspond to what the program is actually doing. It happens to be the right answer, but doesn't correspond to what it's doing. Okay, so those are some examples, but let's see if we can extract some general principles from them. So I'm going to extract 3 general principles from these 3 failed attempts. Before that, let me quickly show you what some good steps look like. So here's the first step, only has one or like it should. And the second step, and notice that the third core step gets skipped because it doesn't correspond to anything meaningful in the surface language. All right, now for the general principles. So let's start with this one. This is the term with the strange extra or in it. So this is disallowed by a property we call emulation, which says that each surface term has to desugar to one of the core terms. And we proved this in the paper in Theorem 1. All right, next, so here's the second core term copied over directly. This is the term that should have been shown in terms of or, but wasn't. And this is disallowed by abstraction, which says that you should show a sugar precisely when the programmer used it. So since the initial program used or here, the step should be shown using or also. And there's a reverse side to this too, which is that if you happened to write something that looked like the expansion of an or, it should be shown as it is instead of in terms of or. All right, and that's theorem 2 in the paper. And finally, coverage says that we should show as many steps as possible, and that's what theorem 4 is about. All right. So that's what resugaring is about. Now let me say a little bit about the main difficulty of resugaring and how compositionality helps solve this problem. Okay, so say that we start with some large surface term that has a 1 plus 2 in it somewhere deep inside as a subterm. And we're going to do resugaring for this. So when it actually runs, first it desugars into some unrelated term, also with 1 plus 2 in it. I'm assuming that plus is in the core language here, so it doesn't need to be desugared. And then this new term is going to take an evaluation step. For this example, 1 plus 2 is the redex, so it simplifies to 3. All right, so now we want to resugar this new term. Now there's an obvious candidate to show, which is the original term, but with a 3 plugged in instead of 1 plus 2. But how can we actually be guaranteed that this works the way we want it to? In particular, if the desugaring of a term was allowed to inspect the contents of its subterms, then this green term on the left might desugar differently depending on whether it has 1 plus 2 in it or whether it has 3 in it. And you might get some completely unrelated term when you desugar it with a 3 in it. So the way we solve this is by adding a condition which is sufficient, which is that to require that the desugaring of a term be compositional. So, or in other words, desugaring should be parametric over the desugaring of a term's subterms. And once we have this, then the green term has to desugar the same way regardless of whether it has 1 plus 2 in it or whether it has 3 in it. And the problem's been avoided. Another way of expressing this constraint is that instead of desugaring terms, you first split a term into nested contexts and then just desugar each context independently. So here's a quick example using the sugar we saw before. So to desugar this, you first split it into nested contexts. So there's a blue context for the ore, a green one for function application, and some yellow leaves. Now to desugar this, you expand all the contexts. And here we just need to do the blue one. And the way you expand the blue context is you pass it to a language-specific expansion function that takes one context and returns another. And we don't place any restrictions on this expansion function. In particular, it can be written in a Turing-complete language. That's fine. And then to desugar the whole term, you just plug the subterms into the new context. All right, so that was composition. Now let me say a little bit about how we dealt with hygiene. All right, so I said the word hygiene, so you know what the rules are. First of all, I have to tell you about all of the terrible things that can go wrong when you start expanding with variables. With variables, and then I have to give you an algorithm that fixes them. All right. Except, come to think of it, though, this is ICFP. So maybe instead, let's take a step back and start with the definition. So the definition I'd like to give, and we can thank Herman and Juan for bringing this back to the forefront. So the definition is that a function is hygienic when it maps alpha equivalent terms to alpha equivalent terms. Now, this does come with a bit of a caveat. It assumes that you have a notion of alpha equivalence over your surface language. On the other hand, it's very powerful. So let me tell you what you can learn from it. So you can learn that if a function is hygienic, then it preserves alpha equivalence. And since it preserves alpha equivalence, it can be thought of as a function over the equivalence classes of terms modulo alpha equivalence. So this means in particular that a hygienic function doesn't really see terms as ASTs with variables in them. Instead, it sees terms as DAGs, where variable use sites point directly to their binding sites. And once you shift your definition of terms from ASTs to DAGs, then hygiene is no longer really a concern. So let me give just a quick example. So here's a let binding around a use of or that introduces a T. Now, if you desugar this naively, then the or introduces its own T that shadows the outer one. And one of the inner T's ends up referring to the wrong place. And this is just a standard example of variable capture. Okay, but if on the other hand, you start by representing your terms as DAGs, then when you expand it, there isn't even the possibility of variable capture because the DAG doesn't even have names in it. All right, now this is a bit of an oversimplification because, of course, ideally programmers would write down their terms as DAGs to begin with, but actually you write down programs with variables in them instead. So we give a resolve function that takes an AST and resolves its scope to give you a DAG. And eventually you're going to want to print these things too. So the DAG keeps the original variable names around, although they're solely there for the purposes of printing. They don't have, at this point, they don't have anything to do with the scope. They're just there for printing. And then we give an unresolved function that takes a DAG and presents it back as an AST. And you might have to do some renaming during unresolution, but the structure of the DAG makes it completely obvious where you have to rename variables. All right, so now let me present the big picture now. Oh, sorry, and we have a theorem that says that you don't have to rename too often during unresolved. Okay, so the big picture is you start with an AST. You're going to resolve its scope to get a DAG and desugar it in the core language. Then it's going to take some evaluation steps in the core language. Some of these are going to be skipped, whereas others can be resugared and unresolved to be displayed as ASTs again. And then this sequence of ASTs you get out is your resugared evaluation sequence. All right. Now, some of you may have seen our paper at PLDI last year. So let me just give a quick comparison to that. So the new thing in this paper, the new things in this paper are, first of all, that we deal with hygiene using DAGs and resolve and unresolve. Second of all, we have slightly more expressive desugarings, since the expansion functions are allowed to be turn complete, although there is that compositionality requirement. And finally, we have somewhat more powerful theorems, although I haven't had a chance to talk about that in this talk. All right, so that concludes my talk, and I'll just put some these theorems up here in case it's helpful for questions.
Is it fruitful to think about desugaring and resugaring as a bidirectional programming problem?
Yes. So the correspondence we actually have is actually stronger than what lenses have, because it's actually a one-to-one correspondence between surface terms and core terms with tags in them, because we have to put some tags to tell you where sugar came from. If you look at our PLDI paper last year, it actually talks about using lenses to deal with sugars that drop some of their variables, and then you actually need lenses to store that extra information.
So maybe you can tell us a little more. You could just go back 2 slides.
Sure.
So 1, 2.
This one?
No. Yeah. Now you have to play the animation so we can. Okay. Good. So there must be something you're not telling us, or that you maybe just very briefly alluded to in the answer to the last question. Core 3 to AST2. You told us before there are many ASTs that might come from it, and you want kind of the one that looks most like AST. So there must be something big that you're just not telling us at all in this talk.
Yeah, so
that you must have remembered how you desugared it in order to remember how to resugar it, or something. How do you do that?
Right. So I'm lying a little bit here by calling these core terms. These are actually core terms with tags on them. And the tags just say where each sugar came from. And so whatever method you use to reconstruct these evaluation steps in the core language, it just has to preserve these tags. So when you desugar, you get back a tagged term, and then for each step, you just need to preserve what the tags are.
Evaluation might introduce a whole lot of new subterms. Right, that comes from the evaluator itself. They don't have tags, do they? Guess so. Or maybe you're just telling. Does it work out to be easy? Are you saying? This sounds like a difficult problem to me.
It's easier than you might think.
Okay.
This part.
For now, but there's many other people. So.
Yeah.
Do you allow, or can your macro system define let? For example, I'm thinking because it's introducing a binding.
Yes, absolutely.
So then, before you've done the macro expansion, how do you know what the binding structure is?
So that was the little caveat I mentioned. So when you write down these sugars, you have to explicitly write down what the scoping structure is for the surface term.
Okay.
Yeah, whereas in most macro systems, that's implicit in the definition of the macro.
All right, so my question is not about the third line, but the second line. And so what's sort of the criteria for knowing that you've got a red X, that you've got something that you're not going to be able to map back? So
we give, in the paper, there's a resugar function, and sometimes it will fail. And basically the reason why it fails is that you've got some term that says it was tagged by coming from, say, like the expansion of a let sugar, and it no longer looks like that, which means that you can't display it in the surface language while still obeying emulation because it has the wrong shape. It no longer has the shape of a sugar. Okay. So those are basically the steps you end up skipping.
I suspect that might be related a little bit to the question that Simon was asking a second ago, that if you've got things that are being generated by the evaluator that don't happen to look like values or terms in the source, is that could also be a reason why you might get an X there.
So evaluators tend not to, so evaluators might introduce new values, but they tend not to introduce new terms. The terms are generally combinations of what was in your original program. As far as values, values are untagged in this, and you can always just display them as they are. So you don't need to worry
there's sort
about
of a
values.
restriction there that your values always have to be sort of surface languagey representable in some sense, which I could imagine not always
yeah.
being true, like for references. Oh.
Yeah. Yep.